Good evening again, everybody. I have made sure this time that my microphone is plugged in so I don't have to record this for a second time. So today we're going to talk about Charles' law. So we did a little bit of studying in the last one about Boyle's law, and that had to do with pressure and volume. And now we're going to add temperature into this equation. So if we take a look at temperature, it's the measurement of the average kinetic energy of the particles. Okay, that sounds like a pretty simple little thing. We've talked about this in the past, that remember average kinetic energy is the amount the molecules are moving. And so when you measure temperature, it is the amount of particles that are pounding or hitting or colliding with that thermometer, I guess it would be down here, sorry, that is actually measuring the temperature. And then obviously the mercury column would increase. And so temperature is a measure of average kinetic energy, the movement of the particles. Particles of all substances at the same temperature have the same kinetic energy. So it doesn't matter what size the particles are, is that they would have the same amount of kinetic energy because the temperature would be the same. Now we have something new to talk about, absolute zero. Not sure how much we've talked about this yet, but this is a temperature at which motion of particles ceases to exist, and this is a theoretical value, meaning that yes, that right now we believe that it's at negative 459.4 degrees Fahrenheit, negative 273 degrees Celsius, or at 0 Kelvin. Now we'll come back to this slide in just a second. I want you to understand how they take a look at absolute zero. So if we draw a simple little graph, and we are taking a look at the volume and we are taking a look at the temperature of the substance. So what they did is they took all kinds of different substances and they cooled them down and they cooled them down and they cooled them down. And you could only cool them down to a certain point, and then they took and they extrapolated and extrapolated the data. And they take another substance and they would do the same exact thing. And so they would cool it down and cool it down and cool it down, and what they found out when they extrapolated the data, it came back to that same point again. It doesn't matter how many substances they tried, they got to the same exact point. And what do you think that point was called? Hopefully you are saying absolute zero. And so what they figured out was that this was at negative 273 degrees Celsius. So matter ceases to exist. What that means is that particles have to be moving to be considered matter. And if you think about it, in the gaseous phase, the particles are moving very, very quickly. In the liquid phase, they slow down. They're just kind of sliding all over each other. Then in the solid phase, they are getting very, very close together where they're basically vibrating. And they continue to vibrate and vibrate and vibrate and vibrate. And they slow down until they reach absolute zero. There is no more movement. There isn't matter. So how close have we gotten to this? We have gotten to 4 zeros after the decimal plate to a 1 in close to absolute zero. It's very, very cold. So if we jump back to this slide here real quickly, you can see that there is a comparison between these. You can see the Fahrenheit, Celsius, and Kelvin, and they all have the 0 point, or the starting point, excuse me. And in 0 Kelvin, there isn't a negative value, which is what we need to have when we study these gas laws, because if we put in a negative temperature, then it might seem like we have negative volume, which we know that can't happen. Water freezes 32 degrees Fahrenheit, 0 degrees Celsius, or 273 Kelvin. And then water boils, and you can see the values there. So how are we going to put this into action? Well, in order to use the next law, we cannot do things in Celsius like I just mentioned, because we will have these negative values. I'm not sure why I have that little line underneath there. It doesn't need to be. It would just be degrees Celsius. So in order to take this into Kelvin, you just take degrees Celsius and add 273, which would make sense because if this is negative 273 degrees Celsius and this is 0 Kelvin, that's what you need to do to convert it. So I just simply need to punch in my calculator negative 45 degrees Celsius, add it to 273, which means I'm actually subtracting, and you should get 228 Kelvin. When you do the same here, add 273, should be 477 Kelvin. If I'm going to go from Kelvin to Celsius, we are going to report all our final temperatures back into Celsius because that's what the rest of the world understands. This, you would take 415 and subtract 273, and I should get 142 degrees Celsius. Again, subtract 273 to get from Kelvin to Celsius, and I get 328 degrees Celsius. Very, very hot there. Okay, so how are we going to use this? Well, we are taking a look at Jacques Charles' law, and he was studying this in 1746. So almost 100 years later after Boyle's law came into focus. So if we take a look, he is describing the relationship between temperature and volume. Now, the reason that this took a lot longer to study is that gases are greatly affected by temperature. So there was a little bit more studying that had to take place here. And what they found out is that this is a direct relationship. So you should recognize that if this is a direct relationship, that if there's an increase in volume, there better be an increase in my temperature. Now again, as I already mentioned, that if we are going to study volume and temperature, I can't have any negative values in here. So again, we are assuming that we have constant pressure and a constant number of particles. Again, this is easy to keep constant, and pressure is the same. As long as you're not taking your container and trucking up to Pikes Peak, you're going to be just fine that the pressure will be constant wherever you're at. So as you take a look, it is going to be the direct relationship of volume over temperature. And if I simply cross multiply, they've done another step here for you. You can see this is a formula that you will often see for Charles's law. And this is on a gold sheet somewhere. You should probably figure out where it is. It's not something that you have to memorize, but this is Charles' law. Keep in mind that it's volume 1 times temperature 2, volume 2 times temperature 1. If you don't like that, you can set up this ratio. You'll just be doing the same thing. Now, the key point here is that you have to make sure that Charles' law is only true if your temperature is in Kelvin. So the temperature must be in Kelvin in order for this direct relationship to be true. So you cannot solve any of these by putting in degrees Celsius or Fahrenheit for that matter. Okay, so let's try an example. So I have a 2-liter sample of air collected at 25 degrees Celsius, then cooled to a new temperature. Again, make sure that you're paying attention to the situation. So I have volume 1. I have 2.0 liters. I only have 2 significant figures there. I have temperature 1 here. I have 25 degrees Celsius. Go ahead and add 273 right away so you don't forget to do that, 273, to get it into Kelvin. And when I do that, I get 298 Kelvin. Remember that when you're adding, it's the first column that there's a guess, and that would be in the tenths or the ones place. So that's why I rounded to the ones place here. All right, then our new volume, it doesn't tell us what that is. That's what it wants us to calculate. And then we have a new temperature that is cooled to 5 degrees Celsius. Again, I need to add 273 right away. And for that, I'm going to get 278 Kelvin. Then I can just simply go ahead and replace it into my formula. So I have volume 1, temperature 2 equals volume 2, temperature 1. So if I go ahead and substitute the numbers, I'm tired of looking at that red, sorry. We're going to put in a new volume, 2.0 liters. Temperature 2 down here, 278 Kelvin. This is the most common mistake people will make with Charles' law, is that they simply will multiply volume times the temperature in the same conditions. Please be careful. So here's my new volume. I don't know what that is, and my temperature is 298 in my original situation. So for both sides, I'm just going to divide by 298. My Kelvin units will cancel out, and I'm left with liters. And as I take a look at that, I have 2 significant figures here, so I need to round my volume to the same thing. So it's 1.9 liters. That's it. These are pretty simple laws right now to start the chapter with. Here's a practice problem for you on page 453. If you get a volume of 22 centimeters cubed, you've done it correctly. And to answer the question exactly, you should say that the bubble is getting smaller. All right, that's it for Charles' law. I only had to record once. Woohoo! I hope you guys are having a great night, and I will see you soon.